Lesson 4 is operations with complex numbers, and complex numbers, we learned about them in lesson 3, but they are usually numbers that involve the imaginary unit I. And up at the top, section 4.1, this goes along with the 4.1 workbook. It is adding and subtracting complex numbers, which is a lot like combining like terms, where you kind of have to look at what the matching variables are. So for example, I'm just going to write this up at the top. You don't need to write this down with me. But if I had, say, 2x and then plus 5 plus 6x, and I wanted to simplify that expression, I would have to see which ones are the like terms, so which ones have the matching variables, basically. So the 2x and the 6x both have an x, so I can combine those. I would combine them by just adding the coefficients, the number in front. So it'd be 2 plus 6 together is 8x, and then I would bring down the plus 5, and I can't actually add or simplify this anymore because the 8x and the 5 don't have the same variable. So that's as simplified as we can get. We would leave it as is, and that's a lot how section 4.1 works. So 4.1, adding complex numbers, I'm going to start on the left side with example 1. So in parentheses, negative 7 plus 6i plus another parentheses, 11 minus 5i. So when we have two complex numbers, this is one, this is another one, separated by a plus sign, the parentheses don't actually really make a difference in the problem. So if you want, you can take them off. So I'm going to rewrite it without the parentheses, negative 7 plus 6i, and then plus 11 minus 5i. So I didn't change any of the numbers, I just took the parentheses off. And then now I'm going to go ahead and identify what are my like real parts of these complex numbers and what are my imaginary parts. So I have a negative 7 and an 11 that are both the real part because they don't have I attached to them. And then for the imaginary parts, I have a positive 6i and a negative 5i, and those are the imaginary parts because they do have I. And I think on the workbooks, they will kind of write this out in some more steps using something called the commutative property. And that property just tells you basically like you can kind of rearrange things. So I can put the real numbers next to each other, the imaginary parts next to each other. But I don't think you necessarily need to write that step. We can kind of look at it and you can highlight or use different, I guess, like underlining techniques to identify the separate ones. Like you can do a line, you can do a little triangle underneath the imaginary parts, whatever you want to do to kind of like differentiate between the different types of numbers. So now I'm going to go ahead and combine my real parts. So that's negative 7 and 11. Negative 7 plus 11 is 4. And then now I can combine my imaginary parts, 6i and negative 5i. I'm just going to combine them by adding the coefficients, which are the numbers in front of the i's. So 6 plus negative 5, or 6 and negative 5 together, is a positive 1. And then the I stays the same. But this is kind of like when you have a 1x, you don't need to write the 1 in front. We can just write it as I. And then we just want to double check that because we're dealing with complex numbers that our answer is in standard form, which standard form is A plus BI. So it's the real part first, the imaginary part second. Ours has the real part first, the imaginary part second, so we're good. So 4 plus I would be our final answer for example 1. And then for example 2, it's basically the same exact problem, the same numbers, except for instead of having a addition sign in between the parentheses, we have a subtraction sign inside the parentheses, or sorry, in between the parentheses. So in this case, I definitely recommend taking the parentheses off, but we do have to do a step before we go ahead and do that. So the first set of parentheses, I'm just going to remove those. I'm not going to change any numbers. So just copy negative 7 plus 6i. And this is only the case when you are subtracting. You just kind of have to do an extra step to kind of get rid of that negative, essentially. So now I'm going to pretend that I don't have a number written in front of here. I just have the minus sign, but I'm going to view that as a negative 1. And then I'm going to go ahead and distribute that negative 1. So negative 1 times 11 is negative 11. and then negative 1 times negative 5i. Negative times negative turns into a positive. And then now my parentheses are off, and I can go ahead and just combine like terms, kind of like example 1. You don't necessarily have to put the 1 there. You can just kind of consider yourself as like distributing the negative. So a negative times positive 11 turns into negative 11, or a negative times negative 5i turns into a positive 5i. It just basically switches the signs of what you originally had in the parentheses. So positive goes to negative, negative goes to positive. Okay, and then now we can identify our real parts and our imaginary parts. So negative 7 and negative 11, those are both real because they don't have I. And then positive 6i and positive 5i are both our imaginary parts because they do have I. So we'll just combine each together. So negative 7 and negative 11, if I combine those, I get negative 18. And then positive 6i and positive 5i together, 6 plus 5, I'm just adding the coefficients, is 11i. And then just double check that it's in standard form. I have my real part first, my imaginary part second, so it is in standard form. So our final answer is negative 8 plus 11i. Sorry, negative 18 plus 11i. Okay, moving on to 4.2. This one has a few different kind of like subsections in it, so I tried to separate them out as best as I could. So the first one is multiplying by a real number, and this uses the distributive property. So for example 1, it's 6 times 3 plus 4i. So the distributive property is when we have a number out in front of the parentheses. I have to take it and multiply it by each of the numbers inside of the parentheses. So first I'll take my 6, multiply it by 3, I get 18. And then next I'll take my 6, multiply it by this positive 4i. So 6 times 4 is 24, and the I just tags along. So plus 24i. So when we're multiplying, I guess, constants by like numbers with I right there, we just have to multiply the number in front. So 6 times 4 is 24, and then the I just stays the same. And then double check that it's in standard form. The real part is first, the imaginary part is second, so we're good. So 18 plus 24i. Okay, and then example 2. Negative 8 times 2 plus 7i. So go ahead and distribute. We have to distribute the negative both times with the 8, so we're distributing the whole thing. So negative 8 times 2, negative times the positive is negative, so it'd be negative 16. And then negative 8 again times 7i, so we're multiplying negative 8 times 7 basically, which is negative 56, and then the I just tags along. So negative 16 minus 56i. And then if you want, I would go ahead and pause before example 3 and then just practice this one on your own and then play once you're ready to check your answer. So example 3 is negative and then parentheses 5 minus 3i. So if you want, you can pretend that there is a negative 1 here and then just distribute a negative 1. So negative 1 times 5 is negative 5. And then negative 1 times this whole thing, negative 3i. So if I do a negative times a negative, that turns into a positive 3i. So negative 5i plus 3i. If you want, you don't have to think of a negative 1 there. You could just think of a negative. So if I'm just distributing a negative, let me kind of erase some of this. If I'm distributing just a negative, it's going to flip my sign. So it changes that positive 5 into a negative 5 and that negative 3i into a positive 3i. So negative 5 plus 3i. And then moving down to the next section, so multiplying a complex number by an imaginary number, so kind of like multiplying different i's together. Before we begin the actual examples, I want to make a table that kind of breaks down the different powers of I, because it does start to repeat in a pattern, and knowing that pattern can help you simplify higher powers of I, like you can see there's this I to the 26th power here. Okay, so on the table, I would pause it and kind of draw the table so you can fill it in as we go. So the first one is just I to the first power. And for the multiplication part, this will make a little bit more sense as we go down the table, but for now we're just kind of gonna state what I is. So I, like, the definition of I is the square root of -1. And then on the right side of the table, the value is going to be kind of like what its simplified form is, basically. So again, this like line probably seems kind of silly when you're first writing it, but it should make sense as we go up in higher powers. So the next power of I would be I squared, which I squared is like I times I. And I times I, or if we were to like say square up here, it would just be squaring the square root of -1. So if I were to take the square root of -1 and square it, that would just cancel out my radical. It would just go away. So technically I squared simplifies to -1, right? So if I is the square root of -1, then I squared must be -1. And then the next one is I to the third power, which I can get to I to the third power by taking I squared and multiplying by one more I. So instead of like two i's being multiplied together, I'm multiplying one more and I have 3 to get to I to the third power. And I can just kind of take each of these like simplified values and put them in here to get my new simplified value. I know this is, just kind of bear with me. I know this is a weird table. So I squared is -1 and then times another I from the I to the first power. So I just replaced I squared with its simplified version. So I squared is -1. I to the first power is just I in its most simplified form. So now if I multiply -1 times I get -I. The next one up would be I to the fourth power, which I can get I to the fourth power by doing I squared times I squared. It's like two i's being multiplied together times another two i's being multiplied together, which each I squared is -1. So this is the same thing as -1 times -1, which is +1. Next, I'll go up to I to the fifth power. So I can get to I to the fifth power by taking I to the fourth power and multiplying in one more I. I know this is a lot of i's. So if I take I to the fourth power, I just found out that I to the fourth power is equivalent to 1. So I'm going to replace I to the fourth power with 1. And then times I to the first power, which is just regular old I. And then now if I multiply 1 times I, that is I. And then next is I to the sixth power. We're just going to keep going up by 1. So I can get to I to the sixth power a few different ways. I'm going to do it by I to the fourth power times I squared, right? So when we like multiply powers at the same base, in this case it's I, we add the exponents. So I do 4 plus 2 to get 6. And then I to the fourth power was 1, we figured that out up above, and then I squared was -1. We figured that out as well. So I'm going to replace I squared with -1. So I'll try to use parentheses once we have the negatives in there. So if I multiply 1 times -1, that's -1. And then next is I to the seventh. I'm going to get to seventh by doing I to the sixth power times I to the first power. So like 6 i's being multiplied together times one more to get to 7. So we just figured out that I to the sixth power is equivalent to -1. So I'm just going to replace that with -1. And then times one more I, because I'm just multiplying in I to the first power right here. So -1 times I is -I. And then the last one is I to the 8th power. And then for I to the 8th power, you could do like I to the 6th times I squared. I'm going to use I to the 4th times I to the 4th. So each I to the 4th is equivalent to 1. So this just becomes 1 times 1, which is 1. Okay, I know usually the first time I show anybody the table, they're like, what just happened? And it's kind of a lot, and there's a lot of ones and I's going around. But the main purpose of this table is to notice when it starts to repeat itself. So if you notice, I go like I, -1, I, +1. And then starting at I again, I go I, -1, I, +1. Sorry, that doesn't really look like a 1. Okay, so after the first 4, it repeats itself into an identical pattern. It goes like, this is the same, this is the same, this is the same, and then this is the same. And it would keep repeating itself in that pattern. So what that means is that we can use like multiples of 4, or we can kind of divide by 4 when we have higher powers, and our remainder will tell us what part of our table our answer matches up with. That doesn't need to mean a whole lot right now, but we'll just get into the examples. So for example 4, I have I to the 26th power. So I really don't want to make this table go all the way up to the 26th power, but I don't have to because we recognize that there's a pattern that repeats every 4. So what we're going to do is we're going to take that exponent 26 and we're going to divide it by 4. So we'll do 26 divided by 4, which we don't want to get like a decimal version necessarily. So if I do 26 divided by 4, that is 6 with a remainder of 2. Okay, and this can be like, you can do long division if you want to. So 26, 4, it's 6, and then this is 24, subtract 2, this is my remainder. But the remainder tells you what exponent on the table your problem matches up with. So we have a remainder of 2. I'm going to go to where I squared is on the table, and my I to the 26th power will be equivalent. So instead of making the table all the way down to I to the 26th, I can just say like, okay, it's going to be equivalent to -1. So this is equal to -1. And basically anytime you have a like power or an exponent over I that is not simplified, or sorry, that is not 1, it's not considered simplified. So if you have like I squared, I to the 3rd power, I to any power, the problem is not finished yet. So you need to simplify it using this table. And I would maybe save like this first part of the table in your notes, or take a picture of it somewhere where it's like easy to reflect back to. Okay, so example 5, now I to the 31st power. I'm going to treat it the same way. I'm going to do not long division this way. I looked at it and it started confusing me. We don't do very long division very much anymore, do we? Okay, so I'm just going to go ahead and take my exponent 31 and then divide it by 4. And it's always divided by 4 because this pattern repeats every 4 times. So that part won't change. You're always going to take your exponent and divide it by 4. So if I divide 31 by 4, that is 7 with a remainder of 3. Because if I were to take like kind of work backwards, if I did 4 times 7, that would be 28, and then I would have to add 3 to get to 31. And then my remainder of 3 is telling me I have to make this match up with my I to the 3rd power, that row. So it's telling me it simplifies to -I. So this whole thing is equal to -I. Okay, so just to kind of like briefly explain, like kind of closing that part out, when you have a higher power of I, or like a higher exponent, you really don't want to make a table that big, but it's not considered simplified and you need to simplify it. So in order to simplify it, you can take the exponent and then divide it by 4, and then the remainder tells you where to look on your table. Okay, I do want to just add one more thing, just in case before we move on to example 6 and 7. This will just be kind of a side note. I just kind of thought if it came up, it might be confusing. Let's say I had I to the 16th power, and if we like divided 16 by 4, that's 4 with no remainder. So if there's no remainder, kind of look at like how if I have I to the 4th, if I were to do 4 divided by 4, that would also have no remainder. So, or I to the 8th, if I did 8 divided by 4, that would also have no remainder. So it's going to match up with those ones that are like exactly multiples of 4. So like I to the 16th is a multiple of 4. I to the 24th, that's a multiple of 4. So it'd finish the same way with all the ones that are also multiples of 4. So 4, 8, 12, 16, and so on. Okay, so moving on to example 6 and 7. These ones have lower powers of I, so that's good. So example 6 is 3i squared times 8 plus 9i. So we're going to use the distributive property again here. So do 3i squared times 8. I just need to multiply the 3 by the 8, and the I squared will just kind of tag along. So 3 times 8 is 24, and then I squared. And then now I'll distribute the 3i squared to the 9i. So same idea, just multiply the 3 and the 9 to get 27. But then I do have to multiply the I and the I. So I squared times one more I, or think of it as like I squared is 2 i's times a third I. So that would become I to the third power. And these two powers, like I squared and I cubed, those are on your table. So you don't have to do any like crazy dividing / like remainder to find those. So we just have to simplify them because they have exponents over I, so it's not simplified. So for the I to the second power, I to the second power is -1. So it'd be 24, and then I'm going to replace the I to the second power with -1. And then for the next one, plus 27. And then for 27, I to the third power, I would go to I to the third power, which is -I. So I'm going to replace I to the third power with -I, and then go ahead and simplify those. So it'll be 24 times -1, which is -24. And then 27 times -I would just turn it into a -27i. And then just double check that it's in standard form. So first, or real part first, and then imaginary part second, 24 minus 27i. And then example 7, I would pause it here and see if you can kind of work this one out on your own and then check your answer after. So I'm going to go ahead and I have to take this -I and distribute it to both the terms inside the parentheses. So -I times 8 is -8i, and then -I times 9i. So a negative times a positive, it turns a negative. And then this is just like a 1i, so it would stay 9. It would just be -9 now. And then if I'm multiplying I times I, that becomes I squared. And then anytime I see an exponent over the I that's not like a 1, and you wouldn't really see that written, it needs to be simplified. So I would go over to my table. This I squared is on my table. I squared is equivalent to -1, so I'd have to replace this I squared with -1 before I simplify all the way. So -8i minus 9 times -1. And then I have -8i. This is -9 times -1, which is +9. And then remember, the real part needs to come first. So this +9i just needs to bump to the front, or sorry, just +9 needs to bump to the front. So we write it first and then followed by -8i, just to make sure that it's in standard form. and the real part comes first. So 9 minus 8i. Okay, example 8. So 3 minus 5i in parentheses times 7 plus 2i. This is kind of like two terms times two terms. So if you remember from Algebra 1, foiling, or sometimes it's called double distribution, we basically just have to take each part in the first parentheses and distribute it to the second parentheses. So the first thing I'm going to do is I'm going to take this 3 and I'm going to multiply it by the 7. So 3 times 7 is 21. And then I'm going to take that 3 and I'm going to multiply it by the 2i. Just remembering now I have to just multiply the number in front of the I. So 3 times 2 is plus 6i. And then now I'm going to take this negative 5i and distribute it to both terms in the second parentheses. So negative 5i times 7 is negative 35i, and then negative 5i times 2i, I would multiply the negative 5 times the 2, so negative 5 times 2 is negative 10, and then I would also have to multiply the I times I, which I times I would become I squared. And then I can combine like terms. I can only combine the i's to the first power because remember, if they don't have the same exponent also over the variable, they're not like terms. So I can go ahead and combine those. I'll bring down the 21. And then 6i and negative 35i together would be negative 29. I need to add the coefficients, and then minus 10i squared, but remember this like squared part is a problem because we can't have any like exponents over the i's in our final answer. And if we go back up to the table, I squared is equivalent to negative 1, so we just replace it with negative 1. So it'll be minus 10, and then instead of times I squared, it would be times negative 1. And just like negative 1, not negative 1 squared or anything like that. And then now I can go ahead and multiply these two together. So I have 21 minus 29i, and then negative 10 negative 10 times negative 1. Negative times a negative turns to a positive 10. And then I can go ahead and combine like terms again. We're almost done. So I have 21 and a 10 that are both like terms because they don't have an I attached to them. So I can add those two together to get 31. And then minus 29i. So 31 minus 29i is our final answer. And you want to write the 31 first, the minus 29i second, so that the real part comes first, the imaginary part comes second, and it's in the standard form. Okay, so the last problem is from 4.3, or last two problems, sorry. So this will go with the 4.3 workbook. And then just remember order of operations. So parentheses is first, exponent second, multiplication and division is next, and then addition and subtraction is last. And just with multiplication and division, and then addition and subtraction, is whichever comes first as you're reading the problem from left to right. So example 1. I'm going to go ahead and jump into it. It's negative 4i times 6 minus 7i plus 12 plus 9i. So I'm going to distribute this. I don't have, I guess, okay, so with parentheses, it's kind of asking you to like simplify what's inside the parentheses first. With what is inside the parentheses cannot be simplified. And then same thing here, because they're not like terms. One is real, one is imaginary. So we can't do anything there. There is no exponents right now, so we can't do anything there. So we have to jump down to multiplication, which we can do because this number is being multiplied by that parentheses. So I'm going to go ahead and distribute. So negative 4i times 6, I'm going to multiply the negative 4 times 6 to get negative 24, and then the I just tags along. And then negative 4i times negative 7i, I would have to multiply the negative 4 times the negative 7, which is positive 28. And then the I times I becomes I squared. And then I'm just going to bring down this 12 plus 9i. I am going to take the parentheses off though because there's no number in front of the parentheses, so there's nothing to multiply in. And then now I want to combine like terms, and I need to simplify this exponent also. So I have negative 24i and 9i. I can combine those. So negative 24 plus 9 is negative 15. And then plus 28i squared, but I need to simplify the I squared. I know that that's the same thing as negative 1, so I'm just going to replace I squared with negative 1. And then plus 12. I'm going to go ahead and multiply these two together now. So negative 15. 28 times negative 1 is negative 28. And then plus 12. I forgot my I on the 15 a few steps ago. I'll go back and explain that again. When I combined the negative 24i and the 9i, I put the negative 15, but I forgot the I. So there should be an I there and here. I'm sorry, I left it off initially. Okay, and then now we have a couple more like terms. We have negative 28 and positive 12, which together is negative 16. And I want to write the real part first, so I'm going to put that negative 16 part first. So negative 16. And then after that, minus 15i. And you can do this in another step if you want. Just remember, you always want to write your final answer as the real part first, the imaginary part second. So negative 16 minus 15i. Okay, example 2 is the last one. So example 2 from 4.3, I'm going to go ahead and zoom in on it. So negative square root of 16 plus 12i minus I times the square root of negative 25, and then in parentheses 3 plus 9i. So I'm just going to kind of start going from left to right. So negative square root of 16, I can simplify the square root of 16, that's 4. So it becomes the negative and then 4. And then plus 12. I'm just kind of copying that down because there's nothing to simplify yet. And then I'm going to go ahead and simplify this part, that multiplication, before distributing it in, because I think that'll save me a little bit of time later on. So first I'll simplify the square root of negative 25. So this is going to be minus I. And then in parentheses, I'm going to put what the square root of negative 25 simplifies to, which is 5i. Right, so square root of negative 25 is, the square root of 25 is 5, and then because I'm taking the square root of a negative, I need to include that negative. And then times, I'm just going to copy down 3 plus 9i. And I think I misspoke before, but just one more time, the square root of 25 is 5, and then if we take the square root of negative, that's where the I comes from. Okay, and then this is technically like all multiplication, so I'm just going to keep kind of simplifying from left to right. I'm just going to copy down my negative 4 and then plus 12i, and then from left to right, this is negative I times 5i, so I'm going to say it's negative 5i squared. So this becomes negative 5i squared, right? The negative times the positive stays negative, and then the 5 becomes the coefficient out in front, and I times I is I squared. And then I'm just going to copy down this 3 plus 9i. And then now finally I have this section like kind of condensed enough to where I can go ahead and distribute it into the parentheses. So I'm just going to keep copying this 4 plus 12i. There's nothing I can really do with those yet because I still have a bunch of multiplying to do in my like order of operations. So I'm going to take this negative 5i squared and distribute it. So it'll be negative 5i squared times 3, which we would do negative 5 times 3, which is negative 15 I squared, and then I'm also going to distribute it to the 9i. So I would do negative 5 times 9, which is negative 45. And then I would have to do I squared times I, which becomes I to the third power. And then now we have a bunch of exponents over the I, so we can go ahead and simplify them using that table. So I'm gonna just kind of keep copying down the 4 and the 12, sorry, the negative 4 and the 12i. And then now we have to get rid of these exponents using our table from up above. I don't think there's a way for me to fit it all on the same page, but just hopefully you can kind of see it together on your notes. So for I squared, that's negative 1. So this is going to become minus 15 times negative 1, and then minus 45, and I to the third power is negative I, so this will be times negative I. Okay, so we're getting closer to the end. So negative 4, keep copying that down, plus 12i, and then this is my last multiplication to simplify my last two. So negative 15 times negative 1 is positive 15. And then negative 45 times negative I is a positive 45i. And then now I can add and combine like terms. So I have my negative 4 and my 15. Negative 4 plus 15 is 11. And I have my imaginary parts, 12i plus 45i together is 57i. So altogether, after all that, 11 plus 57i.